Okay, so welcome to Forces. We're starting 2.2 and we're going to review in this lesson some really basic concepts that you might have come across before. Now, this guy here is Isaac Newton, who completely revolutionized the way that people thought about gravity at the time. In those days, gravity was thought to be an innate property of objects. That means a heavy object will fall because it contained inside it something called gravitas. And what he defined was this idea of a field, right? Where it wasn't the object itself that was heavy, but the fact that it was inside a gravitational field. This is an extremely abstract concept, and in fact many people thought that he was dabbling in the dark arts, and possibly he was. Today we're going to look at this idea of weight and mass, and we're going to calculate weight using a very simple relationship, and we're going to relate the idea of force, mass and acceleration. Excuse the noise, it's advisory and grade 7 is going nuts outside. Right, now this is the wonderful gem that he defined in his Philosophiae Naturalis Principia Mathematica. This was the book that he wrote with all of his laws, of which this one it stands out at this particular moment. It's called Newton's Law of Gravity, and what Newton came up with is a relationship which basically includes all the quantities that affect the magnitude of a force acting on an object in this gravitational field. So any object that's in a gravitational field will be affected by its mass, right? So let's say you've got an apple falling off a tree, then the mass of the apple is important. The mass of the planet it's on, because it's the planet that's creating the field, right? So the mass of the object is important, the mass of the planet is important, and also extremely important is the distance between the two. So the further away your apple is from the planet, the less of a force it will experience. On this note, I wanted to just remind you that Newton stated something which was extremely revolutionary. He stated that every single object, regardless of the size of its mass, had a gravitational field acting around it. So the apple itself has a gravitational field. It's not just the Earth. This relationship is a universal relationship. That means that it applies on the Earth, an apple on the Earth, but it also applies in terms of two planets acting on each other. So the moon and the Earth also have this relationship in place. You and the person sitting next to you, despite whether you're respecting COVID rules or not, will also attract each other using this same relationship. In that case, it would be your mass, the mass of the person next to you, and the distance between you that will cause this gravitational force. In the case of you and the person next to you, of course, this tiny value would be almost insignificant. But it's important to note that all masses have gravitational effects. Now, this is something called the gravitational field constant. And you can look this one up, but it is the constant of proportionality in this relationship. Now, why am I telling you this? This relationship is in topic 6, which we will come to later. But I want you to have a bit of a play with it today, because it explains why, when you travel around the Earth, you actually find that G is slightly different, right? The value of G, which we always call 9.81, varies. That is an average value. If you go to Auckland, Bangkok, Buenos Aires, etc., all of these values adjust slightly to the fact that the height, this bit here, the distance to the center of the Earth is slightly different. If you climb a mountain, you're going to have a different value of G than if you go to the bottom of an ocean. So there is some considerable variety in values. Now, what I'd like you to do is a little bit of research for this first activity. What we're going to do is try and get from here, Newton's law of gravity, F equals capital G, gravitational constant, times m1 times m2 over r squared. What we're going to try and do is get to the relationship that we're more familiar with, which is that the force acting on an object is equal to mass times 9.81, the acceleration due to gravity. I want you to now derive this value here. Now, how do we get from here to here? Well, basically, the mass here in this relationship, F equals mg, is the mass of the object, right? So it could be your mass. You're standing on the earth, so that mass, we're going to call it m2, right? Now, m1 then would be the mass of the earth. That's the mass of the earth. What would r squared be? Well, if you're standing on the surface of the earth, then this r squared would be equal to the radius of the earth, right? And then g is a gravitational constant, which you can look up. Now, what I want you to do when you get to this exercise is you're going to open this Padlet and you are going to add the following information. You're going to write down the gravitational constant. You're going to write down the mass of the earth. You're going to write the radius of the earth, and you're going to calculate this little g value simply by plugging in the values here of m1g over r squared. If you plug in the values here correctly and you end up with 9.81, you will have proven where this F equals mg comes from. Okay, so let's have a look at your Padlet and what you come up with. When you've finished that activity, you can have a look at this video, which is a bunch of astronauts larking about, and a further explanation for how we calculate things. Okay, but basically what this video tells you is how to calculate weight from mass. And I'll give you a quick rundown. That video would be there to supplement what you probably already know. But force, by definition, is the effect of a mass in a field. So it's a consequence of you being in a gravitational field. Mass is the amount of matter in an object. They are two completely different things. Force is a consequence of mass, right? Force is what happens when you have a mass and you put it in the field. This is a nice pretty picture of the field. This is one way of conceptualizing it, like a net that has something heavy in the middle. But basically, this field is what causes the force to happen. And so if you have mass and you're nowhere near fields, if you're a mass floating about in empty space, then you won't have a force, because force is the consequence of the gravitational field. Okay, and that's the basic difference. We will look at this in more detail when we cover topic 6. But for now, calculating weight specifically can be done by using mass times g, 9.81.